Good evening, everybody. We're going to have two little short podcasts for this chapter 11, and I do want to comment that you guys have been doing a great job in catching on to all of this theory, and I hope that this stuff will continue to make some sense to you. Okay, so we're going to talk about atomic size, meaning the radii of the atom, and how do we determine the size of this? Now, we've been talking about, especially we saw that video about the quantum leap and how the argument between Bohr and Einstein and the defined borders and how we are seeing light. And again, we are talking about, sorry, I'm just trying to get this all working here. We are talking about that we have this nucleus in here and we have these electrons that are moving around in this region. And we've been talking about if they're S, P, D, or F, that they're not sharply defined and that they can jump out to an energy level, and when they fall back down, we are going to see light. So in this, we also have a bunch of other properties that we have to discuss, and one of them has to be atomic radii. So for diatomic molecules, you guys know that diatomic molecules, some of them that we've been using a lot are hydrogen, oxygen, nitrogen, fluorine, etc. Fluorine. And so what they do is they use these diatomic molecules and they are measuring the distance from nucleus to nucleus. So nucleus to nucleus, whatever this distance is, then they are able to obviously divide that by 2 and figure out the distance between the atoms. Now again, this is going to be predicted because as we found out is that we can only predict where the electron is 90% of the time. Okay, so if we're going to use some of these trends, it does explain these a little bit more on page 387. There's a nice little box there that does that. But it says that atoms generally increase in size moving down a group. So increase in size, remember in a group we're talking about up and down. These are our families. And if you think about when I go down a family, I am talking about energy level 1. And so we have been saying that that is N equals 1, N equals 2, N is representing the energy levels, equals 3, and so on. And so as we go down our family or down our group, we have greater number of energy levels. We are further away from the nucleus. So greater number of energy levels. And this is going to result in being further away from the nucleus. And so our radius is going to increase. And this should be logical to you. Okay, so that's pretty easy to understand, that they increase in size when they go down the family. We're getting further and further away from the nucleus. We're adding energy levels. Now atoms generally decrease in size, moving from left to right. And this is across a period. So in a period, why are they decreasing in size? Now, this may seem weird to you because as I go across the period, I hope that you be thinking to yourself, well, I am adding more protons and electrons to every element as I go across. So there must be some force of attraction between these, and that's exactly right. So this force of attraction increases So this force of attraction increases, and that means that the protons and electrons are held together very tightly. And so if they are held very tightly, it's just like giving yourself a little squeeze, that results in smaller radii. And so remember that they're moving closer and closer to the right. We're talking about those noble gases that we want to. Good night, Sam. I'll be in a second. Smaller radii as we go across the period. Now, what is this called? This force of attraction is something that's going to be really important, and you're going to hear me talk about it all the time. This force of attraction is called the effective nuclear charge, and we are going to abbreviate that ZEF. I know it's Z, but when we talk about Z, using that for the atomic number and effective charge. So effective nuclear charge, or I'll be abbreviating as ZEF, is that if we add protons and electrons in the same energy level, which is going to be true when you're in the period, in the same period, those attractive forces are held a lot tighter, and it is making the radii smaller. So this effective nuclear charge is going to play a part when we start talking about ionization energy, which is going to be the next topic that we are going to talk about. So just in general, we have these trends, and these are some things that you're going to need to remember, but if you look at your gold sheet, you're going to see you have these general trends on there. So as I go across my periodic chart in the same period, we are going to say that our effective nuclear charge is going to be greater, is going to increase. And then as I go down a family, we know that we are adding energy levels. And that's our principal quantum number. And when we are adding energy levels, that means that our Zeph is decreasing, and this is due to shielding. And so if you think about the electrons due to shielding of electrons from the nucleus. So if you think about, as I add more energy levels, I have electrons further and further and further and further away from the nucleus. Well, as they're moving around, there's electrons that are underneath that are shielding them from the protons. And so then that Zeph, that effective nuclear charge between the protons and electrons, is going to be smaller, and that is going to increase my radii. All right, so you guys have a homework assignment where you're going to graph and answer a bunch of questions, and I hope this will make sense to you. If you have any questions, make sure you bring them to class. Have a wonderful night, and I will see you tomorrow. Where's my record?